Welcome to Easy Gates Electrical Gate 22 paper solutions. The next problem number 27, based on RLC series resonance circuit, and problem based on quality factor. Yes, that's a problem given. So we have an inductor having a Q factor of 60 that is connected in series with the capacitor having a Q factor of 240. The overall Q factor of the circuit is okay. A very simple and interesting problem. Okay, so you need to understand how the Q factor of the inductor is measured, the coil is measured, the practical coil is measured, or a practical inductor is measured, then how the Q factor of the capacitor is measured. Okay, so probably we remember easily the Q factor of the inductor or a coil. So then what is a Q factor? What is the expression governing the Q factor of a capacitor? We should know, then we can connect the two. Okay, so for that, first we need to imagine how the quality factor of a coil can be measured. Okay, so refer the Q factor measurement always referring a series resonance circuit only. So let us take a simple series resonance circuit. Assume this is my coil having a it's a lossy coil having a resistor and inductor, then a tuning capacitor. So assume this is how the Q factor of the coil is measured. So I'm exciting this by an AC signal of certain frequency omega. So then this is my coil whose quality factor is given. Okay, so then tuning this capacitor for resonance. By the time we achieve XL is equal to XC, that means capacitor is tuned, XC is getting tuned, so that when XC matches XL, the circuit is said to be in resonance. Under the resonance condition only, we go for the measurement of Q. So under this condition, the Q is given as omega L divided by R. Okay, otherwise shortly it's basically defined with respect to the energy, but shortly we can go with respect to the power. So it is nothing but ratio of the reactive power of that coil divided by the real, that is I square into R. We can get shortly XL by R. Okay, so let me take this as a R and this is omega L. So it is exactly the impedance is J omega L. Okay, so we are going for the reactive power by the real power. Okay, in the coil where you want to talk about the Q. Okay, so therefore the Q becomes the familiar equation omega L by R. Okay. Yes, let me take the capital R. Usually the small r because we are expecting the resistance to be as small as possible, because ideal inductor should have the quality factor equal to infinity. Okay. Yes, with this we will connect to the problem. So therefore Q1 is given. Q1 of the practical inductor is given. It is equal to omega L divided by R is given. Okay, has 60. So let me take this resistor as R1. Okay, because there is going to be another resistor with the capacitor. There is also going to be a lossy capacitor because its Q factor is also the finite one. So let me take this as omega L by R1 is equal to 60. That is the given data. Okay, that is the first case. Then what is the second case? So how to comment on the quality factor of the capacitor that is given as 240. So let me make this arrangement for the second case. So I have a resistor, I have an inductor. Instead of that, I have an inductor. Then I have a resistor. Call this as a resistor R2, and this is the capacitor. Again, the circuit is excited by the same frequency omega. Okay, then it's easy to connect. Okay, you need to imagine that. Okay, so it is not given in the statement. You need to imagine both the Qs are measured at the same frequency. So this is the capacitor. So here is talking about the quality factor Q2. Let me take capacitor quality factor. So now let me assume, okay, the inductor is variable. Again, I'm going to strike a balance, that is XL equal to XC, to bring the circuit into resonance. It's only the imagination, assuming variable inductor. So then the capacitor is fixed because that is unknown. Earlier the coil is unknown, here the unknown is the capacitor circuit. The lossy capacitor is unknown, that is having a resistance and capacitance in series. It is taken as R2 and C. Okay, So again, what is the quality here means it is going to be Q2 is going to be, again, we can say it's going to be I square into Xc. That's a reactive power divided by real power. That is going to be I square into R2. So then we will end up with I square will get cancelled. So it's going to be Xc by R2. That's a quality factor of your capacitor. So what is that? Xc is equal to 1 by omega C. So it's going to become omega R2 into C. That is going to be the Q2. This is what given for us as 240. So that is the second Q factor. So first Q factor, that is a inductor Q factor, a lossy coil, and there's a lossy capacitor. So given Q1 equal to 60 and Q2 is equal to 240. So if you operate the next setup, that is when we put the two things in series, if you operate the same the new setup at the same frequency, then it's easy to connect Q1, Q2, and the overall Q factor of the circuit. Okay, let us connect this three. Okay. So now let me go for the given circuit. The given circuit is, I have the resistance, I have the inductance, then I have the resistance and the capacitance. So that's a new RLC circuit, again excited by the same frequency omega. So this is a coil, it's having R1, and this is omega L, and this is having R2, this is having reactance 1 by omega C. Okay. So this is J and this is minus J. Okay. Yes, now. So once again, assume the omega is varied and omega is same as the previous omega. Then to obtain resonance, XL should be equal to again what? XC. That means omega L is equal to 1 by omega C. Assuming the circuit is resonance at the same frequency, then this Q is given as Q1. This Q is given as what? Q2. Okay, the Q1 is equal to omega L by R1. And Q2 already determined, that is 1 by omega into R2 into C. So the question is, what is the overall Q of the given circuit? Okay, so Q1 is given 60, Q2 is given as 240. Okay, yes, we'll play with them. So let us make Q as a function of Q1 and Q2. So another easy way is, once again, suppose if you make R2 is equal to 0 in the given circuit, if you make R2 equal to 0, then at the same frequency, you can also confirm. Okay, that's a small verification. If R2 is made 0, again, omega L is equal to 1 by omega C. That is going to make Q1 that is equal to omega L by R1. Okay, that's confirming. Okay, the number is equal to 60 omega L by R1. Suppose if R1 is made 0, then again omega L will be equal to 1 by omega C. That's a mandatory condition. Then we are going for the Q2 Q, because here the capacitor is pure. So here considering pure capacitor and here considering pure inductor. So yes, that is giving a better understanding on or how it is given. Okay, so Q of coil is measured for this condition, and here Q of capacitor is measured under this condition at the same resonance frequency. So that Q2 is equal to 1 by omega into R2 into C. That is given as 240. Now let us go for the Q. So what is the desired Q now? R1. Okay, earlier we made R2 0, R1 0. R2 0 made pure capacitor, R1 0 made pure inductor. Okay, so that I ensured that only one resistor in the circuit. So we can straight away go for the corresponding Q of the coil and Q of the capacitor. Now we are looking for the combined. That means R1 is not equal to 0, R2 is not equal to 0, R1, R2 both are existing. That means now how we can define Q of the circuit, overall circuit, I can say with respect to the inductor, I can say it is I square XL divided by R total, I can say, or nothing wrong in saying it is also I square into XC divided by R total. But anyway, XL is equal to XC once again. So that's a total quality of the circuit, quality factor of the circuit. Let us build from this. So Q1 well defined, Q2 well defined. Okay, let us talk about Q now. Okay, let me take this expression I square XL by R total. So therefore, the quality factor of the new circuit is equal to 1 minute. Yes, it is I square divided by I square, right? So I square will get cancelled. Here also the I square will get cancelled. The result is going to be either XL by R total, that is also equal to XC by R total. We'll go for that. Okay. So Q is equal to XL divided by R total. So it is equal to omega L divided by R1 plus R2, I can say the total resistance. Okay. And Q1, remember it is omega L by R1, and Q2, remember it's 1 by omega R2 into C. So from this, let me go for the values of R1. So from this, what is the R1? R1 can be written as, because I'm looking for R1 and R2. So from this, R1 as a function of Q1 can be written as omega L by Q1. Okay. So from this, R2 can be written as, R2 can be written as 1 by omega C into Q2. That's how we can write. So then the total quality factor, by using this, I can make the total quality factor is equal to omega L divided by, okay, you can substitute R1 plus R2, that is omega L by Q1 plus 1 by omega C into Q2. Okay, that's the expression for the total Q. And not to forget that XL is still equal to XC. That means omega L is still is equal to 1 by omega C. Circuit is still under resonance condition. Therefore, I can cancel these factors. That's an important step we are looking for. So this omega L, and this 1 by omega C will get cancelled because all are equal under this condition. Okay, resonance condition. And then the quality factor turns out to be 1 by Q1 plus 1 by Q2. That will reduce into, take LCM in denominator, it is going to become Q2 plus Q1, and then Q1, Q2 will be the LCM. So numerator is 1. Okay, so this is your denominator. So therefore, the quality factor of the entire circuit becomes Q1, Q2 by Q1 plus Q2. That's a simple proof needed. So now we can play with the data and get the answer. So this step is very important. Okay, so yes, we should get connected to the fundamental, then it is very easy. Okay, this is how you need to imagine yourself first. Okay, so a pure capacitor and a pure inductor setup. You feel like yes, you have to have the same resonance frequency condition, then the next circuit also should have the same resonance frequency condition, then only this is possible. Okay, so now what is your Q? So we can determine Q1 is given 60. This is going to be 240, the whole divided by 60 plus 240, that is going to be 300. So the result is 60 into 240 divided by 300. Okay, so that is going to be 60 by 300 will be 5. So it is going to be 240 by 5. So the resultant Q will be 240 by 5. Okay, nothing but, so 24, it is going to be 4 5s, then 8 5. So it is going to be 48. Let me have a small check. 240 by 5. Yes, that's exactly the quality factor of the resultant circuit using a lossy coil and a lossy capacitor. That's a quality factor. Yeah, interesting problem. Okay, so combining the two Q factors by connecting them in series. Okay, yes. And hope you enjoyed this content, and do subscribe the channel. Will update you with the next problem.